Good morning, everyone. I'm Unyevin, PhD student in AMI Lab. First, I'll introduce the paper named A Unified Analysis of Mixed Sample Data Augmentation, a Loss Function Perspective. This is from MIT and Neighbor. Among the various data augmentation methods, this paper focuses on the mixed sample data augmentation, abbreviated as MSDA. MSDA mixes two samples in terms of their values and labels in a linear combination or a cut and paste manner. Mixup and CutMix is one of the popular MSDA methods. And it is well known that MSDA has surprising performance enhancements, and also they do not need domain-specific knowledge, so they are usually used in various applications. However, this paper argued that still not enough understanding of how MSDA works well. Based on these two papers, this Lee et al. Paper say that Mixup is more effective than CutMix in self-supervised learning, while Ren et al. Say that it argue that opposite results. So in this paper, they try to answer the question that how are Mixup and CutMix different? Before we dive into the paper, I briefly introduce and explain about the Mixup and CutMix methods. Mixup mixes two samples in a linear combination manner. As you can see in this figure, given two images, dog and cat, Mixup linearly interpolate two images like this with the lambda parameter. This lambda parameter is usually sampled from the beta distribution. And the label also mixed in the same way as the images. And this mixer method has very smooth decision boundary compared to the standard method ERM, empirical risk minimization. This orange and green dots represent the data points in each class, and this blue region represents the decision boundary. So as you can see, ERM has very sharp decision boundary, and Mixup has a more smoother one. This smooth decision boundary prevents the model has overconfidence on uncertain examples. So this brings the more generalization ability. And CutMix mixes two samples in a cut and paste manner like this. So in this box-like mask region has image B, and outside of the box region has image A. Images are mixed like this, and then labels are linearly interpolated with the lambda parameter. This lambda parameter represents the ratio between this box region and outside of the box regions. CutMix is also used in detection and segmentation tests, as well as the classification tests. Yes. Let's back into the paper. They try to understand the MSDA method with the theoretical theorems and experimental results. So they propose 4 kinds of theorems that gives you a headache. Let's briefly skim this theorem. First theorem says that MSDA behaves as a regularizer of input gradients and Hessian And second theorem says there exists a mask for any desired regularization coefficients. And also theorem 3 and 4 says that MSDA achieves better adversarial robustness and generalization than the vanilla training. And these theorems conclude that no one-fit-all optimal MSDA. In other words, the optimal mixing strategy depends on applications and data sets and model architectures. And they also propose hybrid version of Mixup and CutMix, H-mix, and Gaussian Mixup, G-mix. Actually, today I do not focus on all this theorem, and I just focus on interpret the theorem 1. And if you want to know more about other theorems and equations or proofs, then you can refer the paper. So this theorem also said CutMix has strong regularization in nearby pixel level distance, while Mixup has regularization regardless of the pixel level distance. With this prior knowledge, let's go to the next one. In theorem 1, they show the loss function of the MSDA. Seems very difficult, but this first term means the loss function for the pure sample that without the MSDA, and other parts represent the regularization term from the MSDA. The paper focuses on these two regularization terms, R2 and R3. This R2 has function G and R3 has function H. This function G and H are derived like this. It is very difficult. It seems very difficult, but we just focus on this part remarked as red. So function G is related to the input gradient, which is first derivative of the function in terms of the input, and it is weighted with the coefficients AJK. And H function is related to the input Tae-Hyun, which is second derivative of the function, and it also weighted with the coefficient AJK. This coefficient is dependent on the mask, as you can see in these equations. Because the coefficient is dependent on the mask, so if we have different design choice of MSDA or the mask, then we can get a different magnitudes of the regularization on the input gradients and Hessian. We can interpret this equation like this, and also we can get this other fact that optimal choice of mask is dependent on applications because target loss function is mingled with the choice of the mask and data sample, and also the pixel level function gradients. So input gradients and Hessians are varying by dataset, test, and model architecture choices. And then they propose H-mix and G-mix to leverage the benefit of both Mixup and CutMix. H-mix is hybrid version of CutMix and Mixup. They CutMix with smaller box region than original CutMix, and then mix up in the area out of the boxes. So this region is CutMix and other region is Mixup. And G-mix is Gaussian Mixup. They select a Feel free to interrupt me. Do you have a question?
Yeah, I have a question in slides before this one. Actually, I'm not an expert in MSDA, and I don't know why do we need regularization terms in the loss function. Can you explain about that, please? I mean, I don't know the role of the regularization terms in the loss function. Does it prevent some kind of negative effects about MSDA or something?
뭘 이해를 못했는지 이해를 못했는데 한글로 설명해 주실 수 있나요?
레귤라이제이션 텀이 일단 이 MSDA에서 왜 필요한지 어떤 부정적인 걸 방지하기 위해서 있는 건지가 궁금했습니다.
This regularization term is not need for the MSDA. It is grounded from the MSDA. So this term is derived with this MSDA. So it is
So I think every loss functions can be interpreted as some kind of high level understanding. So I want to know the role of with this G term and these two regularization term loss functions in high level. What is this functions for?
This G function is in this regularization term too. So this function, and also this function is related to the input gradient. So if we control this coefficient, then we can affect the input gradient. And similar way, H, the coefficient of this in H control the imputation. So what I want to say is this if we change this coefficient AJK with varying design of mask, because this mask coefficient is constructed with the mask mask. So this will bring different magnitudes in here and here. So the strength of regularization effect can be controlled by the design choice of these masks.
So the G and H depend on the Mixup CutMix.
Yes, Mixup and CutMix are also have the mask. So the design of the mask of CutMix and Mixup also affect these parts.
So Mixup and CutMix are both affected to G and H.
Yes.
Both.
Yes.
I don't know. I understand exactly what.
So can you
So can you explain what G and H works in how regularized, what regularized? So I understand the part is consists of also Jacobian and Mixup. So what means G and H in the loss function.
음,
Why is importance
um,
in this?
because this G and H function is the component of the loss function, so this mask design will change the value of the loss function, so it will affect the training process due to the different values. So and also this can be affect the training process.
이렇게 한국어로 해야
아,
한국어로 지금 한 번만
네네.
로스 펑션에 당연히 영향을 미치는 건
아, 네.
아닌데 어떤 영향을 미쳐서 저게 분석을 했는지 하여 아이들로
아, 이게 지금 어떤 영향을 미치는지가
뒤에 나오는
이제 인풋 그레디언트의 G 펑션에 대해서는 이제 인풋 그레디언트에 영향을 미치고, 그리고 H 펑션에서는 이제 해시한 텀이 있기 때문에 해시한 텀에 영향을 미친다라는 것을 그냥 수식적으로 볼 수 있는 거고요.
그 영향을 미치는 건 알겠는데
네.
처음에 하나가 더 지금 같은
네.
이게 아니라 하이어와는 이게 어떤 의미를 가지는지 그래서 국회에서 로스 펑션에 들어가는 뭔가 로스 펑션이 있는지 그냥 없을 때와 있을 때 어떤 차이가 발생했는지
그러니까 이 R2와 R3 텀이 없을 때와 있을 때
그래서 이게 어쨌든 도움이 된다는 점은 그래서 웨이트 레귤라이제이션 하면 웨이트가 작아지면서 필요 없는 웨이트 월스페이스 사라지는 그런 효과가 있고 그런 게 있습니다. 그것처럼 이 레귤라이제이션이 들어가면 어떤 이펙트가 발생하는 뒤에 슬라이드에 있는 아니면 그게 말씀드렸는 것을 놓치는 것이
우선은 이 MSDA를 씀으로써 이제 레귤레이션 효과와 뭔가 제너럴라이제이션 효과가 있다는 건 되게 잘 알려진 사실이잖아요. 근데 아까 인트로덕션에서 말씀드렸다시피 뭔가 어떤 거는 믹서가 더 잘 된다고 하고 어떤 거는 이제 컴믹스가 더 잘 된다고 하고 서로 막 뭔가 주장이 다르기 때문에 도대체 왜 그런 다른 주장이 나왔는가를 그냥 분석을 하는 것 같아요. 그래서 이제 이 분석 결과 컴믹스 같은 경우에는 그 픽셀 디스턴스가 가까울수록 더 레귤라이제이션이 세게 먹히고, 그리고 믹스업은 그거랑 상관없이 모든 픽셀들의 균일하게 이제 정교화가 된다라는 이제 결과를 앞서 말씀드린 거고, 이거는 그냥 수식적으로 로스 펑션을 이제 MSDA로부터 나온 로스 펑션, 사실 이제 제가 앞에 부분들을 다 이제 스킵을 한 건데 논문에 보시면은 이제 그것들을 쭉 일반적인 이런 로스로부터 이제 쭉 이런 식으로 유도를 한 거입니다.
슬라이드에 어떤 파일을 있는지 적힌
그래서 사실 뭔가 이 각각의 텀에 대해서 설명하는 것은 없고, 이제 사실은 이제 여기서 주목하는 거는 이 알파 코에피션트가 이 두 펑션에 모두 들어있기 때문에 이 마스크를 변화함으로써 이제 이 G 펑션과 H 펑션의 값이 바뀌게 되고, 그리고 이 안에는 이제 인풋 그레디언트랑 인풋 해시안이 포함이 되어 있기 때문에 그것들에 이제 영향을 미치게 된다라는 어떤 분석이에요.
그러면 제가 생각했을 때는 레귤라이제이션이 맞는다는 소리. 이걸 막
아,
그렇지만
근,
그걸 리뷰하는 거는
근데 기본적으로 그냥 데이터 어그멘테이션 중 하나이기 때문에 뭔가 오버히팅을 막는다거나 그런 레귤라이제이션을 일반적으로 기대하고 있고, 그래서 이 페이퍼에서 뭐 딱히 특별한 어떤 레귤라이제이션 효과를 바란다라는 거는, 네, 그런 건 없습니다.
그러면 그 레귤라이제이션 텀이 이제 레귤라이제이션 텀이 의도적으로 추가한 게 아니고 이제 그냥 그 제너럴한 MSTA 텀에서 데리베이션이 있는 거죠.
그렇죠.
데리베이션을 하고 보니까 그게 그레디언트랑 해시안의 변화를 갖는 거고 제 생각에는 그냥 직관적으로는 그레디언트가 슈링크되는 효과를 줘서 뭐 오버피팅 같은 걸 먼저 볼 수 있을 것 같아요. 그거랑 스트랩의 디스턴스 이런 거랑 어떤 뛰어난 원에 나왔던
그거는 이제 나중에 약간 실험적으로 다시 한번 보여줄게요. 뭔가 수식적으로는 그냥 언급만 되어 있고 왜 그런지에 대해서 사실 제가 서플리멘터리를 보지 않아서 잘 모르겠긴 하지만 막 명확하게 나와 있지 않아서 그냥 실험적으로 나중에 말씀드리겠습니다.
하나 더 궁금한 게 그전 펌 슬라이드에서
어떤 거 말씀이시죠?
거기 여기서 그 그레디언트 앞에 그레디언트가 있잖아요. G.
아, 네.
그래서 그거랑 이제 트랜스포저에서 멀티플리케이션 하는 이것도 해시안이랑 관련이 있잖아요. 그거에 대한 언급은 해시안과 관련이 있지 않나요?
관련,
그레디언트랑 그레디언트 트랜스포저에서 GX 멀티플리케이션 하는 해시안과 좀 관련이 있어요.
그냥 논문에서 언급하기로는 사실 인풋 그레디언트의 프로덕트라고 그냥 표현하고 딱히 뭐 해시안과의 연관성 같은 거는 언급하지 않았고, 그리고 제가 생각했을 때도 좀 다르지 않나요?
G가 그레디언트가 치는 G랑 G 트랜스포저를 매치해서 멀티플리케이션 하면 해시안이랑 관련이 생기는
그게 해시안의 어프록시메이션이라고 알고 있긴 한데
그래서 그 G도 사실 해시안이라고 말하는 그런 거 때문에 그런 언급은 그런 상황이죠.
뭐 해시안의 어프로시메이션이라고 말씀하시니까 그렇게 생각해도 될 것 같긴 하지만 논문에서는 굳이 그것과의 연관성을 언급하진 않았고 그냥 인풋 그레디언트 프로덕트와 관련있다라고 되어 있습니다.
감사합니다.
And then they compares the different MSD design choices in 3 ways. The first one is in terms of the values of the regularization coefficient AJK. In this figure, x and y axis denote the pixel distance along each axis. As you can see, this Mixup has equal weight to every component, and CutMix has high regularization in closer coordinates. And other hybrid methods, such as stochastic mix-up and CutMix, which do mix-up and CutMix alternatively, and the proposed H-mix and G-mix have intermediate coefficient values. So with this figure, we can visualize the strength of the regularization with this coefficient by these coefficient values. And second one is the input gradient value. This figure also has x and y axis, which denotes the pixel distance along each axis. And note that this figure do not show the accuracy of the model, but the input gradient values. So compared to this mixup method, CutMix in this region has relatively lower value. So it means CutMix reasonably regularize in the input gradient products when the pixel distance is small. So you can strongly regularize with the large coefficient AJK to the closer pixels. And lastly, it is about the best choice of the mask design can be varying by the target task settings. To show this empirically, they designed two scenarios. The first scenario is smaller object by large crop size, and the second one is larger object by small crop size. In the first scenario, they crop a large region, 80 to 100% of an image, and then they resize to 64 by 64 resolution. So the small object is retained small, so the closer distance relationship might be more important to accurate classification. As we assumed, the results show the CutMix performs better than Mixup. And in scenario 2, they crop a smaller region, 25 to 40% of an image, and then also resize to 64 by 64 resolution. Then this object will be extended, so the larger distance relationship might be more important. So as we assume, the Mixup performs better than CutMix. So in conclusion, any MSDA method behaves as a regularization on the input gradients and Hessians, which means, and also the degree of the regularization is controlled by the design choice of MSDA or mask. And they also compare various MSDA methods in three ways. First one is regularization coefficients, and second one is regularized gradients, and last one is model performance in various scenarios with different pixel level importance. And they also propose two simple MSDA methods, HMix and GMix, to leverage the benefits of Mixup and CutMix by CutMix. I did not show the experimental results, but it showed that HMix and GMix outperforms other MSDA methods.